Okay, the next situation we look at is kind of a long paragraph describing this, but we have a circuit that looks like this. Here's our upper left, lower left, and the instructions say, well, we're going to put a certain resistance between upper left and upper right, between upper right and lower right, etc. When we follow those instructions, we end up with the circuit that we show here. A 20 ohm resistance between upper left and upper right, a 10 ohm resistance between upper right and lower right, 25 ohm resistance between lower right and lower left, and a 10 volt source between lower left and upper right. Now we label those points A, B, C, and D for easy reference. They weren't labeled in the instruction in the document, but we went ahead and labeled them. Here we also have a resistor connecting upper left to lower right, or A to C, and that's a 15 ohm resistance. Now, we're going to have three different currents running in this circuit, and it's not difficult to understand why. We're going to have some current, let's just start from upper left, we're going to have some current that goes through the 20 ohm resistor, and that's going to be the same as the current that goes through this 10 ohm resistor, because there's no place for the current to go from between here and here, except to go directly through both of these resistors. Okay, so any current that goes through this resistor has to continue on through this one until you get to C, at which point that current can split up, combine with the currents here and here in some way that we're going to have a little bit of trouble with if we don't come up with some rules. Okay, so there's one current. I just labeled that I1. We don't know what that current is. We're going to come up with some rules that allow us to develop a set of equations, a system of equations that we can solve to find these currents. We're going to have another current here, call that current I2, and another current here, call that I3. In labeling these currents, it doesn't matter whether we have them in the right direction or not. We're going to get some equations that we can solve for I1, I2, and I3, and if we happen to have chosen the wrong direction, we're going to get a negative for that current, telling us the current goes in the opposite direction. It's not going to be a problem. Okay, now this particular circuit could be analyzed as a series combination of a 10 volt source and a 25 ohm resistor with a parallel combination of your 15 ohms and your 20 and 10 ohms. And of course that 20 and 10 ohms could be combined into a 30 ohm resistor, since that's just a series. Okay, I'm going to leave them separate because the next thing we're going to do is we're going to run a wire from here to here, and now those resistors won't have the same current running through them. Okay, so in order to analyze this, we need a couple of simple rules, and it's fairly easy to reason out these rules. First rule is, if we follow any path through this circuit, let's just say the path from C to D to A and back to C, that's a closed path in the circuit. We're always within the electric field. Okay, electric field of whatever device it is that we're running current through, but we have the same electric, well, we have a continuous electric field throughout this loop. And since the electric field is conservative, then the voltage drop around the loop, the voltage change around the loop is zero. So if the voltage change is zero, the voltage drop is zero. We usually talk about voltage drop. You'll see why in a minute. That just means if I start from any point and go around a loop back to the same point, well, since this field is conservative, there's no change in potential energy. And voltage is potential energy change per unit of charge. Okay? So, since there's no potential energy change, there's zero potential energy change per unit of charge, zero voltage change. So this is just an expression of the fact that the field is conservative. Okay, now, there are three loops in this circuit. Okay, I asked everybody to find them, so you ought to think that through if you haven't already done so. Yeah, got to point them out. Now there's one here from A to B to C back. Actually, we'd want to go this way because the traditional way to run a loop is counterclockwise, just kind of keeping in hand with right-hand rules and stuff like that, and other conventions. You don't have to run them counterclockwise, but it's often a good idea. So we have this loop here that runs, if we go counterclockwise, D to C to A to D, and this one C to B to A to C. We also have the loop that goes around the outside. That's a perfectly good loop. We don't have to confine ourselves to a loop, to the smaller loops. We could use the big loop here. But the thing that we've got to be careful about is this big loop out here is actually a sum of these two small loops. Okay? If we add the first small loop that goes this way, well, and the negative of this loop going this way, we get a big loop. And you want to think about that a little bit, but those loops are not linearly independent, to use to slightly adapt a term from linear algebra and differential equations. Okay, so there are three loops. I've listed them here, but only two of them are independent. Any two of them would be independent. Any two of these loops can be combined to make the third. The loop around the outside could be combined with one of the loops around the inside, either add or subtract, depending on the situation, and you get the other loop. Okay? Okay, the other thing is the total current into a branch point is 0. What do I mean by that? Well, here's the branch point A, where the circuit branches off. B is not a branch point. The circuit doesn't branch there. The current has no choice about where to go. When it comes up to B, it's got to keep going, and it can't split off. If the current comes up to point A, it can split off into current here and here. Now, total current into a branch point has to be 0 because the branch point can't accumulate charge. Okay, these are conductors. They can't accumulate charge. There's no capacitor here. So charge can't build up within the conductor. So that in this case we would say the net current into point A is what? Well, from the directions I3 comes into A, so I3 is into A, so that's I3 is part of the net current into A. But I1 and I2 go out of A, so we have to subtract them. So it's minus I1 minus I2. That's the net current into A. And it's equal to 0, again, because current can't accumulate at A. The net current into C. You can work that out yourself. It's I1 plus I2 minus I3. Are these equations independent? No, they aren't. Okay, they're not independent, they're equivalent. If I multiply this equation by -1, I get an equation that's equivalent, that's identical to this equation if I just rearrange my terms a little bit. Okay, so these equations are not independent. If you tried to write the equations corresponding to the voltage drops across the three loops, they would not be independent either. Only two of them would be independent, and only one of these would be independent. However, note that if we get an equation for any two of these loops and this one equation, either this one or this one, then we have three equations and we have three currents, so we have three equations and three unknowns, and we can proceed to solve and find the currents I1, I2, and I3. Now these rules that the voltage drop around a loop is 0 and that the total current into a branch point is 0 are called, now how do we pronounce this? I've heard it pronounced, Kirchoff. Sounds like somebody sneezing. Kirchoff is probably closer to the correct pronunciation. I've heard that. Most Americans just say Kirchoff. Okay. I'll probably use both pronunciations. I've gotten used to Kirchoff, but you know, I'm butchering some pronunciation. I don't know if that's Russian or Polish or German or what, but I'm probably being pretentious if I say kirchoff, because I really don't know how that's supposed to be pronounced. I might as well just use kirchoff, which I know isn't right, but it's what everybody says. Anyhow, those are the two laws. We're going to apply them to this case where we connect A and B, or D and B, with just a bare wire, and see what that does to the situation.